Okay, so I am gonna discuss another problem from TIFR 2020 PYQ. So this is from nuclear physics, basically radioactivity, and this is a very long question. Many statements are given. Okay, so let's try to read what they are trying to say. So there is natural potassium contains radioactive component of 40K, that is 2 decay modes. So this is a radioactive component 40K and 2 decay modes. The first mode is it is going through a beta decay to the ground state 40 Ca, and in the second mode it is going through a electron capture to a excited state 40 Ar and following by a single gamma transition to the ground state of 40 Ar. So it going through beta decay, one decay mode, and next it is electron capture and then gamma decay. Okay. So the amount of radioactive 40K in a natural potassium atomic weight is given sample is known to be 0.0118%. So if you have given some potassium sample, natural potassium sample, so this much percentage has the radioactive 40K. Other are not radioactive. So this much percentage is radioactive. Okay, and it is also known that in the decay of 40K, so 40K is a radioactive element, it will decay in two mode, the beta and the gamma. If for every 100 beta particle emitted, there are number of gamma photons emitted is 12, so 12. So if you have a radioactive 40K, if it will total number of decays is 112, then out of this 112, there will be 100 beta particles and 12 gamma photons. Okay. So this is the statement they are trying to make. Okay. And now they given that if the number of beta particles emitted per second by a 1 kg natural potassium is 2.7 into 10 to the power 4, then what is the mean lifetime? Okay. So pause this video, read this question carefully again and give this problem a try by your own and then look at the solution. Okay. So lot of things you have to do. First try to find that what is the number of particles in 1 kg natural potassium. So you have given 1 kg natural potassium and what is the number of particles in that. And your atomic weight is 13.089 and this is in gram. Okay. So 13.089 gram of natural potassium. Okay, natural potassium contains in a number of particles. Na is the Avogadro number. Okay. So what is 1 gram contains? 1 gram contains simply Na by this 39.089. So what is 1 kg contains? 1 kg contains is equal to 1 kg means 10 to the power 3 gram. 10 to the power 3 into Na divided by 39.089. Okay, so this is the number of particles in 1 kg of natural potassium. So let's calculate this. So just take my calculator. This will be 1.5408 into 10 to the power 25. So this is the number of particles present in 1 kg natural potassium. Now this number of particles is not radioactive. Okay, so in question it is given that among natural potassium this much percentage is radioactive, so you have to find what is the number of radioactive particles of 40K present from this number of particles. So you have to multiply this by, so number of radioactive particles is point zero zero, sorry, not point zero zero, point 0118. Okay, so point 118 percentage, so divided by x, so into this number. Okay, so what will be your number of radioactive particles? This will be uh, 1.818182 into 10 to the power 21. Okay, so this is the number of radioactive particles. Let me write a little bit clear. 8182 10 to the power 21. This is the number of radioactive particles. Okay, now there comes the important part. So this number nr will decay, but in two decay modes, the beta and the gamma. So if total beta plus gamma is 112, then out of this 112, beta will contain 100 and gamma will contain 12. Okay, this is given in the question. and your final thing is given that number of beta particles emitted. So you have to multi. So among this NR, 100 by 112 will be the number of beta particles it will emitting. Okay, so this will be the number of beta particles it will emit. I mean, the fractional number of the fraction of NR which will emit beta particle is this, because out of 112, 112, 100 particles will be beta particles. Okay, so this is the fraction of parent nuclei which will decay into beta particle. Okay, so this into 1 minus e to the power minus lambda t, because number of decays you have to find. If you multiply it by e to the power minus lambda t, this will be the particles that survived. So you have to calculate the number of decays. So it is 1 minus e to the power minus lambda t is equal to simply 2.7 into 10 to the power 4. It is given. So what will be and your NR will be, your NR is previously calculated 8182 into 10 to the power 21. So 1 minus e to the power minus lambda t. Now this also is given that it is 1 second. The number of beta particles emitted per second. Okay. So you have to put simply t is equal to 1. So it is to the power minus lambda just. Okay. So t is equal to 1 is equal to, so 1 minus e to the power minus lambda t is equal to, just put these things in right side. Okay. And this will be is equal to something, what will be the quantity. But let me try to give you some insight that this is a very large quantity, 10 to the power 21 order. So if you divide by NR, then this will be extremely small quantity. Okay, so this quantity, the right hand side quantity, is extremely small. So you can approximate this e to the power minus lambda is 1 minus lambda. Okay, e to the power x is equal to 1 plus x square by 2 factorial, this kind of thing. Okay, so you can simply just write it as lambda. Okay, because this right hand quantity is extremely small. So lambda is simply will be given by, just put this quantity right side, it will given by 1.66 into 10 to the power minus 17. Okay, so this quantity is extremely small, that's why I am doing this approximation. Okay, so this is your lambda. Now you have to find the what is the mean lifetime. Remember, you don't they don't ask you to calculate the half lifetime. Okay, if it is half lifetime, that is log 2 by lambda, but they are trying to ask the mean lifetime, so it will simply be 1 by lambda. Okay, so mean lifetime is simply 1 by lambda. So that will be equal to, it can calculate 6.0125 into 10 to the power 16. But this is in second. They are asking you in years. Okay. So just simply divided is by 1 year contains 365 days and 1 day contains 86400 second. Okay. So that will be years. So your answer will be 1.9 into 10 to the power 9. So this is the answer for half lifetime. And if you do this silly mix test that they are asking you mean lifetime, if you calculate the half lifetime by mistake, if you use this formula log 2 by lambda, then you will arrive at 1.3. So you can take this 1.3 and do the silly mistake. You do all the great job, and by simply doing a silly mistake, you can arrive at this answer. So be careful. Be careful at the statements of the question that they are asking mean lifetime. Okay. So yeah, this is a, I mean, long statement like a JEE type problem. Okay, from radioactivity. Yeah, that's all for today. Thank you.